Good day. For this particular makeup session, I'm going to start out with the homework that was assigned last week, and we have from page 43. And this particular section involves separable differential equations. And for what we have in problem number 3, we have a derivative, dy over dx is equal to y times the sine of x. And we're looking at solving for y. In this equation, we can separate the variables. And so we can divide by y and multiply both sides by dx. So here we have dy over y is equal to the sine of x dx. And we have, upon integrating on both sides, we're going to end up, for the antiderivatives, to the left, we will have the natural logarithm of the absolute value of y, and placing the constant to the right, we have equal to the negative of the cosine of x, followed by the constant. In terms of solving for y, now we can eliminate the presence of the natural logarithm if we take both sides, upon which we will raise the natural logarithmic exponential base e. So we're going to have e to the natural logarithm, the absolute value of y, is equal to e to the negative cosine of x plus c. So we have for e to the natural logarithm of the absolute value of y, this will go to the absolute value of y. And in looking at what we have in the context of the product property of exponents, now we will have e to the negative cosine of x times e to the c. And in looking at what we have here, e to the c, you have a constant raised to a constant, and a constant raised to a constant is still going to be a constant. So in making the adjustment, we have for the absolute value of y, we're going to have is equal to a constant times e to the negative cosine of x. Now for the next phase, there will be some seeming redundancies. Now upon taking out the absolute value notation, okay, so we're going to have y, and this will be equal to plus or minus c times e to the negative cosine of x. And again, regardless of whether it is positive or negative, a positive or negative constant is still going to be a constant. So we have for the final solution, okay, we have for y, you have, once again, c times e to the negative cosine of x. For what we have in the case of the next item, and let me give you just a bit of a segue here. And we're looking at, in the case number 10, we'll be looking at taking integrals of reciprocals of squares of binomials. And now just a little bit of a recap. Say we have in the case of integrating, which we're going to do. Okay, and let's say if I have something like the integral of dx all over the square of 1 plus x. So I have for dx over the square of 1 plus x. Okay, so we're going to have 1 plus x to the negative 2 dx. And again, this is just a little revisiting the power property of integration. Okay, and so you have 1 plus x to the negative 2 plus 1, which would be negative 1. And we have all over negative 2 plus 1, which would be negative 1. And so this will come down to the negative of the reciprocal of 1 plus x followed by the constant. Now, in the case of what we're going to have for number 10, and we have for this particular differential equation, so you have the square of 1 plus x dy over dx is equal to the square of 1 plus y. Once again, we can separate the variables. Okay. So on one side, okay, we can have ny, just rewriting, so we have dy all over the square of 1 plus y is equal to, and once we multiply by dx and divide by the square of 1 plus x, we get this following statement. And now upon separating, we can now integrate on both sides. And just looking at the above property. Okay, so for the reciprocal of the square of 1 plus y, so we're going to have the negative of the reciprocal of 1 plus y. And once again, we'll have to the right, we're going to have the negative of the reciprocal of 1 plus x, followed by the constant. And so, and what we have in this case, I can change the sign of both ends. So I have 1 over 1 plus y is equal to 1 all over 1 plus x. Okay. And again, now change the sign value of the constant. Okay, so we still have to be a constant. Now, if I combine the terms together to the right, so I have 1 over 1 plus y. And we have, in terms of combining the terms to the right, so just putting c in terms of a fraction. And we have upon combining, and the reason I'm doing this is so I'll be able to take the reciprocal of both sides and also be able to isolate y. So joining the two terms together to the right, I have 1 plus c times the quantity of 1 plus x all over 1 plus x. Now, in taking what I have now, if I flip both sides of the equation, so I'm going to have that 1 plus y is equal to 1 plus x all over 1 plus c times the quantity of 1 plus x. and just taking away 1 from both sides. So we'll have for y itself, so you have 1 plus x all over 1 plus c times the quantity of 1 plus x minus 1, and you can just leave it in this particular form. Okay, and again, I just don't want this to be like complex fraction overkill. So for y, okay, so we're looking at the general solution, and for this display, as far as I'm concerned, this is going to suffice.